Physics Penguin.
Hello and welcome to Physics Penguin's Guide to Special Resistors. We're going to look at how different electrical components behave in a circuit today, and we're going to use graphs of current and potential difference to see what they do. As always, there is a worksheet in the description of this video that you can use to check your understanding. Last time we used Ohm's law, V equals I times R, to calculate what happens in electrical circuits. This time we're going to need this formula, so let's remind ourselves about it. V is potential difference, sometimes called voltage, measured in volts. This is energy for every little charge that flows through the circuit. So high potential difference means that charge passes on more energy if you touch it, for example. So touching a high voltage cable is going to hurt. I is current. This is how quickly charge is flowing. This seems similar to potential difference, so think of it like this. Thought experiment. Cue strange music. Imagine that you have to cross a road in a strange land. There are no cars, just a stream of animals, one after another. The speed of the animals is like the current, but stepping in front of a line of kittens is not the same as walking into a line of stupid walruses. It's like the kittens carry less energy into you because they're small, so they are low voltage charges. But the walrus traffic is high voltage. Okay, well that was weird. Hopefully you get the idea. Current is to do with how quickly electric charges move, but PD is all about energy. The third part of the formula was R. That's resistance, and that's how hard it is for current to flow through a material. Whatever value R has, if you increase V, you are forcing the charge to try and move with more energy. So you would expect to see more current, and that's all Ohm's law says. V equals I times R. So I equals V over R, which means that if you double the PD, you should double current. If you double resistance, you should halve it. The thing is, not every material follows this rule. Many do much of the time, but the ones that don't are really interesting. Righty-ho, well let's have a look at some of these interesting components, starting with the wire. Okay, well it's not super exciting, but it is a good place to start. Let's have a look at its imaginative and thrilling symbol. Oh, don't judge, it does look like that. As long as it doesn't overheat, the wire is going to follow Ohm's law. It's very important for physicists to hide their knowledge behind confusing language, so we like to say the wire shows ohmic behaviour. Let's look at a graph of the current compared to the potential difference. If you think about it, the gradient, the steepness of this graph, is related to the resistance of the wire. Steep graphs have low resistance, and flatter graphs have high resistance. The graph shows a line with one gradient or steepness. It doesn't change. That means the resistance doesn't change. That means that the wire is ohmic. Look what happens if the PD is negative. Well, current is negative, but the resistance is still the same. This is super easy unless the wire gets hot. So let's look at that next. Next component, please. Chicks and assorted sea life, please welcome the filament lamp. Also known as the light bulb, as long as it's the old-fashioned type with a little wire in it. This symbol is just the latest of several for the lamp and is easy to draw. It's just an X in a circle, but personally I don't like it. We used to use one that actually looked more like what it is, but then ordinary people started understanding our subject, so we had to change it. Let's look at the current PD graph for the filament lamp. It looks like a badly drawn S shape, but what does that mean and why? Well, the steepness is changing, so that means the resistance is changing. Look more closely. Low voltage and current is in the middle of the graph. This is where the line is steep. Steep means low resistance. At high currents, both positive and negative, the graph flattens. This means high resistance. So why does this happen? Why would the resistance increase when the current goes high? It's hard to answer because we can't see it. So let's use my wonderful model again. If current is like the flow of traffic on a road, then what happens to how easy it is for these big stupid walruses to move? If lots of them are trying to move quickly down the road, it'll get harder, right? Now we can't see the electric charge flowing, but we can see its effects. What happens to the lamp if you turn it up high enough? Well, it glows, right? Why? It's glowing white hot. Heat is the answer here. Thermal or heat energy is escaping from our electric circuit because we've got too much current in a small wire. If I don't want this to happen, I could use a thicker wire, which would be like a motorway for all those walruses. Wow, this is getting weird. Anyway, electric filament lamps and electric heaters work like this. So remember the S-shaped graph, and remember this is caused by resistance increasing when the wire gets hot. That's really important. Some materials are just plain weird when you put them in a circuit. Back in the 1940s, humans started to mess around with materials called semiconductors. These are made from elements like silicon that are basically bad electrical conductors, but you can add other elements too to make them conduct, but only under special circumstances. One of these first semiconductor devices was the diode. Cue diode. Well, let's have a look at the symbol and the graph. The symbol is a circle with an arrowhead in it. The arrow is a one-way sign. The diode lets current travel in only one direction. Now let's look closely at the graph. The whole left side of the graph is flat. Flat means infinite resistance. Infinity is a bit of an awkward number in maths, but it's easy in physics. I equals V over R. So any value of potential difference is going to be divided by the biggest number there is. Anything shared by a huge number means each share is basically zero, so no current flows. On the right it gets more interesting. The graph goes steeply up. In reality it's very steep, and we normally have to add a resistor next to our diode, or else the current spike will get way too high. The interesting part of the graph is on the right, but before the line goes up. There is a short part where the PD is positive, but no current flows. We call this the threshold voltage. Remember, PD is to do with energy. Time for another overly convoluted mental model involving animals. This time let's use squid. No, not squid. Dragons. No, too scary. Let's have badgers. So, the badgers are like electric charges, and they are moving through a wire just like walking over a field. Then they come to a river. The river is the diode. Badgers can't swim. Their fur gets really knotted. But in a diode, one of the banks of the river has a shop run by a cow called Eric, who hires canoes. If the badgers arrive at the opposite bank, well, too bad, no canoe shop. But if they arrive at the right bank, all they need is enough energy to wake up Eric the cow, and then they can hop in a canoe and paddle to the other side. Thus, badgers can flow one way through the diode/river canoe thing. Totally clear. If you listen to a diode close up, some do say you can hear the snuffling of badgers and the gentle mooing of a cow. But those people are crazy. Righty-ho. Now you'll need to have a go at the worksheet from the description below. Pause the video and then unpause when you're done. This stuff is quite tricky. Let's see what we can do. Welcome back. Let's have a look at the worksheet. This is based on a past paper question, so it's a good gauge of the difficulty of your GCSE paper. Question 1. A student wants to investigate how the current in a filament lamp affects the resistance. Describe how the student could use her circuit to investigate how the current through a filament lamp affects its resistance. The first part of this is all about understanding what the examiner wants. Let's give a thorough answer. Let's make up a circuit diagram and include a voltmeter and an ammeter to measure V and I. Once we have that, we need to describe the change of the brightness of the bulb and explain how Ohm's law will give us the resistance. The question does not ask about what increasing the current does to resistance, just how to measure it. Okay, so we need a circuit to light a bulb and including the 2 meters. It also has to have a way of increasing current. We could use a potential divider circuit here, but we haven't used them yet in this series. So I'm just going to use a variable resistance in series with the bulb. This resistor can have a big resistance or a small resistance, or anything in between, so it will reduce or increase the current for us. Thanks to the Institute of Physics for the circuit diagram, by the way. So we have a 0 to 12 volt power pack in series with our variable resistor, the lamp and the ammeter. In a series circuit, order doesn't matter, so you could place these components wherever you like, within reason. The voltmeter has to go in parallel though, and we want to know the PD across the bulb, so we place it across the bulb. Notice the old symbol for the bulb, by the way. We seem to use the X in a circle now, although that was really for indicator lights. So you need the diagram. What next? Well, you have to say what you would do. You'd set up the circuit, measure the current through the bulb and the PD across it and record the values. Then you would change the resistance of the variable resistor and repeat the readings. If we increase and decrease the resistance of the variable resistor, we could quickly get at least 5 values of V and I for the lamp. Finally, how would you show the data? Well, you could work out the resistance using R equals V over I, but a better way is to make a graph of I on the y-axis and V on the x-axis. The shape of the graph will tell us how the lamp behaves. That's quite a long answer, and there is quite a bit to do there. If you struggle to nail the detail, don't do what a lot of people do at this point and leave the rest of the question, because that was the hard part. So the next part. Describe how the resistance of a filament lamp changes as the current flows through it. Easy. We're even given a graph of the data, so we don't have to learn anything here. Just use the information we are given. Look at the graph. As the current on the x-axis gets bigger, resistance on the y-axis goes up. Now we have to answer like an intelligent penguin, so let's phrase it properly. The resistance increases as current increases. That would be fine. If you want to be a real smarty, you could even say that the relationship is not proportional, because the line curves upwards, so any further increase in current would give a much greater increase in resistance. Don't explain why this happens, the question doesn't ask. Part C is an estimate from the graph, so there is a little wiggle room here. Let's use the graph again. It says use the graph to estimate the resistance of the filament lamp when a current of 0.1 amps is going through the lamp. So we need to find what R is when I is 0.1 amps. Just look at the graph. Oh dear, the line doesn't go down to 0.1 amps. We can still give an answer. Let's just continue that curve back to the start of the graph. It should get flatter and flatter as you go back. If you trace back, I think the line is crossing the axis at about the second little line above the 6 ohm mark. There are 5 of the marks between 6 and 8 ohms, so each mark must be 0.4 of an ohm. So my estimate would be 6.8 ohms. However, as long as you are less than 7 ohms and above 6.4, I think you'd be fine. Penguins are good at wiggle room, it's how we walk. Last section 3 is just more graphs. Easiest part, I thought. Graph A shows something where the steepness of the graph, the gradient, gets smaller when we use a bigger PD. This is where a wire is getting very hot and increasing resistance, so this must be the lamp. Graph B shows a constant gradient or steepness, so that would be an ohmic conductor like our unheated resistor. And graph C only allows current in one direction, so that has to be the diode. Also, it's the only one left, so there's that too. Well, I hope you understood all that. It's fine to go back and watch again if you're getting stuck. Thanks for giving it a go. If you find these videos useful, please subscribe and you will get notified when the next one goes up. Until next time, ta-ta from Physics Penguin.
Physics Penguin.